Hi everyone, welcome to the webinar. We'll probably just give it a couple more minutes before everyone joins, and we'll probably start in like a few more minutes. Thanks, guys. Thanks for waiting.
Hi everyone, I'm Riddhi, your host for today. We have Ayman as our telecom security expert. If you have any technical glitch or any issue, you can let me know in the chat box down below. Also, we have parked 10 minutes in the end after the presentation for a question and answer session, so you can write down your questions in the chat box or in the question answer box below. And we will also be sharing a copy of the recorded webinar post the session. So in case you missed out anything, you can always go back and refer to it. And now over to you, Ayman.
Thanks, Reddy. Hello, everyone. Thank you for joining the webinar. Today, we are going to talk about data exfiltration using the SS7 protocol stack. So who we are? I'm Ayman Elsehiri. Over 12 years of experience in cybersecurity, focusing in telecom domain. I work as a telecom cybersecurity expert at SecurityGen, specializing in performing telecom security assessment for mobile networks and researching the security of telecom protocols and technologies. Now, let me handle the floor to Sebastian for the introduction.
Thank you, Ayman. Hi everyone, my name is Sebastian, and I have been previously active in the telecom industry for over 15 years. So now I'm basically a senior pre-sales in SecurityGen, and I'm mainly like managing the customers across Asia Pacific region. So my past experience mainly is across the multi-domains solutions, including like mobile fixed solutions, securities, and also the telco cloud infrastructure. So for today's sessions, we have Ayman, our SME, basically to share to everyone regarding to some of the recent threats and also a little bit about the current incidents, the recent incidents. And also, he will also share some of the data exfiltrations approach via various of tunneling techniques. And then eventually we will also introduce some of the mitigation recommendations. And of course, the sessions will be eventually ended with some Q&A sessions. So without further delay, I will pass it back to Ayman. Ayman, the floor is yours.
Thank you. So let's get started. As we have seen in recent years, cyber threats continue to evolve and target various sectors. One area that has received significant attention is the telecom industry. Recent security incidents have shown a growing focus on this sector, and in many cases, attacking groups demonstrated deep understanding of telecom networks and the protocols, how this network works, how they are interconnected with each other, and the deep understanding of the technologies used by this network. For example, the ABT group Salt Typhoon compromised at least 9 US telecom companies, and the operation went undetected for about 1 or 2 years. The group gained access to sensitive data, such as call recordings, SMS, call metadata. They even recorded calls of high-profile targets in the US by exploiting local interception systems. Even more concerning, a recent report by the French cybersecurity agency revealed that attackers had compromised mobile core networks and even satellite systems across multiple operators in France. This report highlights the use of custom code developed specifically for telecom protocols used by these actors. An ABT like Liminal Panda leveraged IBX network, which is used to interconnect mobile operators globally to target operators across multiple countries. One notable tactic by Liminal Panda is the use of telecom signaling protocols in a non-traditional way. Unlike most attacks targeting these protocols, they used signaling for command and control communication and data exfiltration, which is the primary focus of this webinar.
Hey, Ayman, before you proceed, maybe you can share some thoughts. Like, is there any specific reasons like why you focus on Liminal Panda or Salt Typhoon?
Yes, sure. Our main focus is on recent incidents that involve telecom-specific technologies and network features. And this is why we are bringing up those ABTs. And for Liminal Panda, it stands out mainly because the tactics were deeply tied into the telecom technologies and the protocols. Unlike most other attacks, which start with traditional IT systems like exploiting known vulnerabilities or gaining access to some privileged accounts, the initial access point was the IBX network. They also developed their own custom tools that's able to capture and decode telecom traffic and the protocols and extract sensitive information from the core network. They extracted information from nodes like SGSN, which handles subscriber data traffic, for example. And on top of that, they abused, as I highlighted, they abused the SS7 and GTP for data tunneling, which is something recently or new to them.
Understood. So basically, the technique is very, very focused and relevant to telecom industries, right?
Yes, exactly.
Okay, thanks.
So what is data exfiltration? Typically, once a group gain access to a network, they need a way to communicate with an external server, which is usually called C2 or command and control server. This communication is required in order to receive instructions from this server to be executed and to extract data out of the network. This was typically done over protocols like DNS and HTTP, mainly because outbound connections for these protocols are typically allowed in enterprises and mobile networks. However, this also means that these protocols are closely monitoring for security abuse. But what sets Liminal Panda apart is the use of SS7 and GTP for this activity, completely bypassing the traditional monitoring on DNS and HTTP traffic. So before we begin, what is GTP? GTP is a protocol used in mobile networks. It's originally from GSM, but it's still widely used in LTE and even 5G networks, mainly to support mobile data access for subscribers. Because it's a tunneling protocol by design, attackers can easily repurpose it into tunneling data out of any network or compromised network. For example, Liminal Panda simply used an open source GTP emulator called SGSNMU to create fake data sessions on behalf of non-existing subscriber from the target network they already compromised, allowing them to to tunnel data over GTP, and they make it look like a legitimate user is just surfing the internet or performing some traffic. The tool was installed in one of the network elements, which was compromised, and created this GTP tunnel. The tunnel was created over IPX and reached the C2 server, and they started after that to extract data and send data out of the compromised network. The tunnel can be created either directly to the C2 server. They just create a GTP tunnel with the C2 server, which is published or accessible through IPX, or it can be through internal nodes like BGWs. This tool can establish a BDP session with this node and start accessing or sending data to the C2 server over the internet, not the IPX. This is the way to access or open these tunnels. For SS7, they used a similar approach, but unlike GTP, SS7 is not a tunneling protocol. In addition, it's a more complex protocol, not as simple as GTP. So the group had to develop a custom tools. It's called the SIP translator, which is capable of tunneling data over SS7 protocol. Although SS7 is a legacy protocol, its complex binary nature offers attacker an effective way to hide exfiltrated data. So using the same techniques, they established the tunnel over IPX to the C2 server. Once established, they started to exfiltrate data out of the target network.
Hey, Ayman.
So,
Sorry, before you
yeah,
proceed, can you back to the previous slide?
okay.
Yeah, thank you. I think because we have various of audience today in the webinar, basically I think it's clear about the core network topologies and also the C2 APT control network. But could you share a little bit more information about what is this IPX network is?
Yes, sure. IBX or IB Exchange is a private global network used by mobile operators mainly for roaming and interconnection to support services like voice calls, messaging, and mobile data. Some confuse it with IBX protocol, which was an old transport protocol developed by Xerox, but it's completely different. This is a network used by operators. Unlike the public internet, IBX was designed specifically for telecom traffic. However, access to and from IBX on the mobile operator side is often not as strict or as secured or monitored as traditional IT networks, which make it more attractive for threat actors. I hope this made it clear what is IBX.
Yep, it's definitely clear for me. Thank you.
Okay, thank you. So back to SS7, we are going to discuss what is the SS7 stack, what is important protocols that can be used for this purpose. So SS7 is not a single protocol. It's actually a stack of protocols developed in early 1970s. It was originally designed for fixed line calls, but later extended to support mobile telephony features like subscriber mobility, SMS handling, and online billing. The stack follows a structure similar to the OSI model. These kind of models are usually used in order to separate network connectivity into separate layers, and each layer will be handling a specific part of the functionality, usually making it totally isolated, as you can see. The lower layers are usually managing physical connectivity and network transport, this part, while upper layers are mainly responsible for application data or application services. Now we will briefly go over the key protocols needed to understand how tunneling can be achieved over SS7.
I'm sorry, stop you again. Just wondering, like, since the previous slide you have mentioned the SS7 protocol has been started since 1975. It's such an old technologies, right? So, like, why is it like still widely being used nowadays? Yeah.
Okay, correct. Indeed, the SS7 is an old technology, and it's still in use today, mainly because many operators continue to support 2G and 3G networks for multiple reasons. For example, these networks often provide more coverage than newer generations, especially in rural areas. Also, in some countries, certain devices like IoT devices, such as the smart meters, vehicle trackers, and etc., rely on 2G and 3G networks. This is why it's still in use. Even in some countries, some subscribers are still using old features phone, which doesn't support newer technologies like LTEs and 5G. Additionally, SS7 remain critical for interworking and roaming. Even if some operators no longer use 2G and 3G on their own network, they still need to support their customers or subscribers when traveling abroad to location with these technologies are used. So it's critical and still used even for interconnection.
Understand. So as long as the world has not like sunset the 2G and 3G, basically it's still gonna be active for a while, right?
Yes, exactly.
Okay, thank you.
So the first group of protocols highlighted in blue are used mainly for legacy SS7 or the transmission of SS7 over all the TDM links. It consists of message transfer part 1, 2, and 3, which are mainly responsible for physical connectivity and transmission over TDM. The second group, highlighted in green, are used for SS7 over SecTran. SecTran is a family of protocols introduced by Internet Engineering Task Force. Its main purpose is to allow sending SS7 traffic over IP networks instead of legacy links like TDM. Together, these protocols represent the lower layers of SS7 stack. The next one is SCCP, or Signaling Connection and Control part. It mainly provides routing of signaling messages between network elements and handle features like flow control, segmentation, error correction and detection. SCCP implements some functionality of the network layer or SI model, mainly for routing messages. In traditional IT networks, routing is based on source and destination IP addresses. However, in SS7 network, SCCP uses different identities. Mainly, routing is based on something called the global title and signaling point codes. Global title is often used between different operators or over IPX. Global titles are addresses that looks like normal phone numbers, which are assigned to unique network elements so that other network or other elements can address it by this global title. The next one is TCAP, or Transaction Capability Application part. This layer lies between the SCCP layer and the upper layer like MAP or TCAP or CAP. It provides transaction mechanism for the upper layers. For example, it allows two network elements to open concurrent dialogues, send multiple concurrent messages related to different activities, and the TCAP will be able to correlate responses to the corresponding requests for these messages. The final layer we are going to discuss today is MAP, or Mobile Application Part. It's an upper layer protocol, which is used by various network elements. For example, it's used to access services in nodes like HLR, which is a central database storing subscriber profiles and information, nodes like MSCs, VLR, and other SS7 nodes. It mainly enables services related to mobility, subscriber mobility, handling of calls, SMS delivery, and location-based services. So now let's.
Sorry to stop you again. Can you go to the back, to the last?
Yes, sure.
Yeah. So like it's such a complex protocol stack for the SS7s, and there's like so many layers of stack of the SS7 itself, right? So based on your experience, like which part of the SS7 protocol basically is the most dangerous or the most exposed part of it, and what could be some of the most common attacks on that? Yeah.
Okay. Usually the upper layers. SS7, as you mentioned, is a legacy old protocol. It was designed based on a flawed trust model between telecom operators at this time. It's indeed vulnerable to critical vulnerabilities that can lead to issues like interception of incoming and outgoing calls and SMSs, locating subscriber location, fraud and denial of service issues. For the lower layers, such as MTP and SCTP, they require direct access to the node to be able to be exploited. However, for higher layer protocols like TCAP, MAP, CAP, and SCCP, those can be targeted remotely over IPX. So mainly the upper layers are considered the more dangerous because they are exposed to more attacks.
Okay. Thanks for the explanations.
Now let's explore in more details how SS7 can be leveraged for data exfiltration. As I highlighted, SS7 is a complex protocol and there are various methods for tunneling data over it. We will focus on techniques that operate at the intermediate layers like SCCP and upper layers like TCAP and MAP. Mainly our research focused on this layer because the lower layers like MTPs and SCTPs uses fixed rigid format and provide low capacity for data embedding, making them impractical for data exfiltration. However, they can still be used for low traffic purposes, such as command exchange with C2 server, for example, which doesn't require high volume of traffic. I will begin with the most easily detectable tunneling methods, then progress towards the more stealthiest ones. Okay? One way to embed data into SS7 is by defining a custom upper layer protocol to carry these data. So someone can define their own custom protocols and use it above the SCCP layer in order to tunnel data over this intermediate layer and completely replacing layers like TCAP and MAP. However, doing so often results in clearly malformed messages, which can raise red flags and they can be easily detected by monitoring tools, which is exactly what we want to avoid. So a better approach is to add or append the data to a valid, legitimate SS7 message. Data is usually added after the end of SS7 message to tunnel data beyond the map layer, after the map layer. As you can see, this is the upper layer. We have a packet with some valid TCAP and the map layer. Then we use this part in order to append data to it. We call this method message tailing. Okay. Let's take a look at a sample PCAP to see how this can be achieved or how it looks like. As you can see, we have a standard SS7 message. This one is called send routing info for SM. This message is used to get routing information for subscribers in order to support SMS delivery. Here we see the normal message structure with MTP layers, SCCP, TCAP, and the map with some information or some parameters added to the map layer. But if you check the raw message view in Wireshark, this part, you'll see that after the message ends, there are some extra data appended to the message. This data can be any kind of data, it can be binary data, but for this sample, we choose to exfiltrate some text data. It mainly represents information about some subscriber, its MZ, IP address, and location represented in the form of cell global identity. This is the identifier for the cell that the user is currently attached to, which can be translated into a GPS location with some accuracy using some online services. Even though this packet is altered, and doesn't fully comply with specification, it's still viewable and decoded by many elements, even by Wireshark without any issues, and it can travel through SS7 network without any issues. That's mainly because intermediate nodes in the core network that handle message routing, like STBs, for example, only inspect lower layer and intermediate layers, like SCCB, in order to route the message. So when this message is sent over the network, most intermediate nodes will only check this part in order to forward the message to the next destination. This is why such kind of messages travel normally in SS7. Also, for demonstration purposes, we added the data in form of clear text. Normally, when someone is exfiltrating data over any protocol, they are transferred in encrypted form to avoid detection. But here, for this demo or this sample, we are adding it clear text to be easily viewable. Also, one thing to highlight, in order for the message to appear correctly or parsed correctly by tools like Wireshark or even by network elements, it's not just about appending the data to the end. You need to alter multiple parameters included in different location, which represent length of the message, some pointer to the message, to be able or to avoid producing a totally corrupted message. So this technique is a little hard to detect by even conventional signaling security solutions, as many of these solutions are looking for specific attack signatures and usually ignore data beyond the expected message boundary. The data capacity for this method is limited by the maximum SS7 message size, specifically the SCCP message type. For the standard, or so the usually used SCCP message, which is called the unit data, it can carry up to 255 bytes. And for some special kinds, like long unit data, it can carry up to 4 kilobytes. Okay? This will be similar to data of over 16 subscribers transferred in a single message. It can carry this information, MZ, IP, and cell global identity of 60 subscribers in a single message. Okay? Now imagine if an attacker is trying to exfiltrate data, let's say about 100,000 subscribers. It will likely take about 1,600 messages. So is it a big volume? While volume of normal international traffic varies between MNOs, an average of 8,000 to 10,000 messages per second is typically considered normal. So it's really tiny compared to the normal traffic generated by mobile operators on daily basis or even per second. It will be like a needle in a high stack, which means that it's hard to spot by defenders. The next technique, we call it the SCCB gap tunneling. In order to understand how it works, let's have a closer look at the structure of SCCB messages. This is how SCCB message looks like. It consists of multiple parts. The first one called the message type code, which define which SCCB message is included in this packet. And then, depending on this code, each message type has a specific format. So for messages that carry upper layer payloads like TCAP and the MAP, which is the usual message sent in SS7, it includes two parts. A part called mandatory fixed part, which includes some flags and some parameters about the SCCP message itself, like its protocol with its class 0, 1, or 3, 2, or 3. Then we have a mandatory variable part with most of the parameters included in this one. This mandatory variable part, from its name, or as the name implies, it includes mandatory parameters. All the parameters need to be there, but they have variable lengths. It includes parameter required for routing, such as called and calling party addresses, in addition to data from upper layers like TCAP. So for an SCCP decoder, in order to understand this message, For the fixed part, it is simple, mainly because each parameter has a defined length. It can read them sequentially. But for the variable part, it needs a way to know the length and the start of each parameter. This is done through special pointers added to the fixed part. As you can see, it has 3 pointers, and each pointer points to the start of the variable length parameters. We have a pointer for the called party address, called, and data. So by manipulating these pointers, we managed to create a gap. We simply increased the value of the pointer that points to the upper layer data with some bytes that is more enough to embed some data, and use this gap to add some hidden data inside the message.
Hey, Ayman, sorry, just out of my curiosity, is like, yeah, back to this slide basis. Is the hidden data have to be always like after the calling party address, or it can be resides in basically anywhere?
No, it can be anywhere. It can be before any parameters. By manipulating the pointer, you can create a gap before called the party address or between these two anywhere in the SCCP message.
So basically, the security solution such as firewall, it needs to have the intelligence to basically detect wherever that it appears, right?
Yes, exactly.
Okay, thank you.
So this is how it looks like over Wireshark. Again, we are using the same message, send routing info for SM. This is the standard layers of the protocol. As you can see, if you check the raw message view, you can see that the data is embedded between the protocols, exactly between the TCAP and SCCP part. So for this technique, detection is more difficult because the data is embedded between the layers. And as Sebastian highlighted, it can be between any parameters, not just in a fixed location. And this type of technique or this type of tunneling will generate compliant messages that will not be detected by any node and do not introduce any notable change. What makes it worse is that the old SCCP protocol specification didn't clearly disallow these kind of gaps. It was a gray area, it was not mentioned. Although recent versions prohibited creating gaps in SCCP parameters between SCCP parameters, for the receiver part, they mandated that the receiver need to be able to handle gaps, mainly for backward compatibility in order to support any node or node that generates older packets with some gaps. It has the same data capacity as the previous technique, which is limited by the SS7 message size itself. I even tried to estimate how many tweets from Elon Musk, for example, can fit into a single message. And guess what? It's about 14 tweets that can be embedded in a single SS7 or SCCP message. Another technique involves embedding data into parameters of upper layers, such as map or TCAP. Usually, SMS and USSD related messages are good candidates for this, as they already contain user-supplied data, making the tunneling appear as legitimate, for example, legitimate SMS sent by a subscriber, which make detection more challenging. But for greater stealth, we choose to split the data across parameters in different layers of protocols, and which we call cross-layer tunneling. In this example, we have a bunch of send routing info for SM responses, which is a response for the previous message. This message is used to support SMS delivery. It usually contains information about subscriber. So for example, in case of SMS home routing solution implemented, it will contain information about correlation ID for this subscriber, its identity that will support delivering this message to the subscriber or the target user. It also includes the address about the home router solution or the SMS anti-spam solution so that the message will be delivered to him. Sometimes there are other optional parameters like LIMSI, which is a temporary identity that is used to identify subscriber in a serving node, like VLR. And for the TCAP layer, in order to support transaction, it includes some parameters like the destination transaction IDs or source transaction IDs. Now let's check how we can embed the same subscriber data into these response packets. We have already explored the techniques that can be used to tunnel large amounts of data with moderate to high stealth, but this time our primary goal is to remain undetectable, or at least achieve maximum possible stealth. So we utilized the location node number or the parameter which holded the SMS router global title in order to embed the subscriber MSISDN. We added this data over here. Okay. And for the parameters that hold the correlation ID, we embedded the MZ of the subscriber that we are exfiltrating its data. And for the cell global identity, which carries the location information, its length was longer than the remaining parameters, like destination transaction IDs and other parameters. So we split this part into two parts. The first part of the cell global identity was encoded in the destination transaction ID, which is 4 bytes. And the second part was included in the LIMSI parameter. Okay. So at the receiving end, the exfiltrated data is reconstructed back by combining all of these parts. So we have the same information, which we try to exfiltrate using other techniques. For this technique, although the data embedding capacity and the encoding options are more limited with these techniques, mainly due to the constraint of the maximum size and format of the parameters that are used for this exfiltration. For example, in this sample or the previous sample, the maximum amount of data that can be tunneled in a single message was 60 bytes. And some parameters like the network location or the address of the SMS router must be numeric. So this adds more restriction. However, this approach offers the best stealth available among the all techniques we have discussed. Data is scattered across multiple parameters without introducing any non-compliant messages, closely mimicking normal SS7 traffic. Additionally, we selected a message like send routing info for SM, since a large number of these messages are common in networks, making the exfiltrated data difficult to detect. So far, we have discussed 3 different tunneling techniques. Some offer maximum stealth, but with limited capacity, while others allow for higher data throughput at the cost of reduced stealth. We discussed message tailing, SCB gaps, and cross-layer tunneling. Given the limited focus on monitoring outbound signaling traffic, we believe even achieving maximum stealth may not be necessary for adversaries because actually no one is looking at this traffic at all.
Hey, Ayman, sorry, like just questions from my side regarding to all these tunneling techniques, right? So it seems like basically the cross-layer tunnelings will be the most complicated or the most complex one because of the
Yes.
highly stealth approach, right? So
Yes.
yeah, I'm just wondering, like, is there any specific technique or specific logics required in the maybe in the firewall in order to detect such attack? And maybe you can also suggest any other approach or protections that could be done to avoid this attack.
Yes, sure. Usual techniques that embed data into parameters of upper layers, especially when they are scattered, like in cross protocol tunneling, are among the most stealthy method and are difficult to detect. Detecting such techniques require behavior-based analysis that mainly focus on deviation in traffic rate, timing, and the message size, for example, and traffic pattern, rather than relying on static rules or message format validation, for example. We will explore how such tunneling can be detected by a tool like TSG shortly after the upcoming demo.
I understand. Thanks. So basically, it means like simple firewall may not be sufficient, right? You may need various of,
Yes,
yeah. Okay, understand.
exactly.
Thanks.
Now it's time for a demo. During this demonstration, we will see how the SS7 can be used to transfer a file from one machine to another. On the right, we have an agent, a virtual machine with an agent installed inside it that will handle the tunneling part with access to some secret data. This data can be any binary file or text file. On the left-hand side, we have a C2 server on a different machine that will be receiving this data. So at the top of the screen, you can see a virtual machine representing the command and control server, which is set up to accept agent connections over SS7 and handle decoding of the received SS7 messages. It supports tunneling data using multiple techniques. For this demo, we will use SCCP gaps. At the bottom, we have tunneling agent that will be used to transfer a secret file located within it. Also, network traces will be captured so that we can exactly see what's being transmitted over the network. Now C2 is starting and ready to accept connection. The agent will send this file, secret_data.txt, to the server over SS7, encrypting the data with some predefined key to avoid detection in network traces. So it started to send data. As you can see, in Wireshark, the traffic looks like normal SS7 exchange between two network elements. Those are some send routing info for SAM messages, which were used for SMS delivery. Okay. At first glance, the packets structure appear ordinary with the standard layer, SCCP, TCAP, and other layers, with the required parameter in each layer. Okay. However, if you check the raw message view in Wireshark, okay, this part represents the end of SCCP layer. Okay. Now, when you check the TCAP layer, this part represents the start of the TCAP layer. Notice that TCAP layer is not directly appended to SCCP. There is a gap between them. And this gap is where the agent is embedding the data. Okay? Since the data is transferred in encrypted form, it's no longer viewable even in Wireshark traces or manual views, making it looks like normal SS7 messages. Since the data is now transfer is complete, this is what was received on the server, C2 server. The subscriber information, same information we're talking about, is now transferred from the agent to the server. So I hope you enjoyed the demo. Now,
Hey,
okay.
Ayman, we have very interesting questions actually related to your demos just now as well, because you are showing the C2s, you are simulating a C2 servers just now, right? So basically the question is regarding to like, can the IPX provider actually identify the C2 servers? And additionally, what should be the role of the IPX providers in terms of security or preventing any kind of malicious data tunneling for these C2 servers? Do you mind to share some thoughts on that?
Yes, sure. Mainly the main issue with these kind of messages is that, as we saw, the embedded data travels in a standard SS7 messages in encrypted format. So it's not easily possible by IPX provider to detect such attempts. For the IPX, the C2 servers looks like an ordinary SS7 node in the network. It can be thought as a normal HLR in some networks, which is sending some SMS-related messages, mainly because the messages are not malformed and data encrypted within inside it. So this covers the first part. For the second part, can you please repeat the second part of the question?
Yep. The second part of the question is basically like, what is the role of IPX provider in terms of like preventing this kind of malicious tunneling for these C2 servers? Do they play a role on that?
Yeah. Usually, IPX providers only provide the basic security filtering. As far as I know, no IPX providing is doing something for this tunneling issue because it's very advanced. However, they provide basic filtering for signaling protocols. For example, for the diameter protocol, they perform some filtering on which messages or which application IDs are allowed over IPX and which are not. They perform checks like spoofing checks, but those are mainly basic security checks. They don't provide advanced checks like this. And as I highlighted, even traditional security signaling security solutions that can be deployed on the mobile side with a basic signature or role-based approach will not be able to catch this technique. So something new or a dedicated solution is needed for these cases.
Okay, understand. I hope it's answered clear the thoughts of the whoever that raised the question. Thank you.
So now let's discuss the mitigation strategies to detect and prevent tunneling over SS7. We will focus on preventing first unauthorized access over IPX network. Then we will detect how these techniques or tunneling can be detected. Okay. Well, to tunnel data, an attackers need a path to the T2 server. An attacker may attempt to a direct SecTran or SS7 connection over IPX and address the T2 server by IP address directly. Therefore, it's critical to restrict the traffic at the IP network edge to only your border STPs and authorized IPX provider only. This can be done using IPX firewalls, which is a typical network firewall installed at the edge of the IPX from the operator side. From observation, IPX firewalls configuration are often too permissive, frequently allowing traffic between root subnets, especially for GPRS part of the network or GTP part of the network. Even in some cases, we have seen management protocols like SS7 or even Telnet accessible over IPX for some operators, which demonstrate that access over IPX is not strictly managed in the same way as other part of the network, like the internet or other part of the IT network of the telecom operators. So this is the first step. You need to restrict which nodes can access IPX network. Another option for attackers, since your border STP already have access to IPX, an attacker can connect your internal STPs directly and reach the C2 server, but in this case, using global title addressing in the SSCP layer. No direct IP connectivity is required. So it's important to ensure your STPs only accept connections from trusted internal nodes by enforcing ACLs or source binding. The good thing is that this is typically in place, but it's important to verify it. Okay. Finally, the same techniques can be applied to diameter, other protocols like diameter and GTP, where you can restrict the IPX access and access to your internal nodes like DEAs and the GTP nodes the same way. Sometimes controlling access isn't enough. For instance, an attacker may have already compromised a core network element that has access to IPX network directly. So a defense in depth strategy is recommended. It's essential to have a signaling-aware security monitoring in place to detect any tunneling activity. Although the tunneling techniques we discussed didn't produce clearly malformed messages, some of them still deviate from protocol specification. So a strict format validation using a whitelist approach can help detect and block many of these tunneling attempts. For example, for messages that contain extra data beyond the message boundaries, it should be flagged and rejected. Similarly, for SCCP gaps, it should be monitored for some time once you are confident that none of your internal nodes are producing the gaps by mistake, for example, then they can be safely blocked. You typically begin by implementing this validation in monitoring mode to minimize false positives and manually detect real incidents. Once you are confident enough with this result, you can switch to blocking mode to block these attempts automatically. However, most stealth techniques may evade this format validation, so it's essential to monitor and detect anomalies in signaling messages as well. Now let's look at how an advanced signaling security solution like TSG can go beyond the basic format validation, message format validation. We will discuss how tunneling attempts, when embedded with normal signaling exchange, can still be identified and blocked. On the right side, we have an MNO network with some agent installed for data tunneling, while TSG is monitoring all IPX traffic at the left. Once TSG is deployed, it creates a baseline that includes, among other information, a list of trusted internal nodes that is authorized for IPX access. So if a known network element is trying to send a traffic, for example, this MSC is trying to send update location message, TSG will inspect the message. Okay, this node is a trusted one, part of the baseline, and it will be allowed. Now, when the agent is attempting to embed data using some highly stealth technique, for example, in this case, the agent is trying to send embed data in USSD messages in upper layer protocols. Now, TSG will inspect the message. It knows this is a new node that is not part of the baseline, so it will block this access. Additionally, TSG continuously monitoring inbound roaming activities to support some advanced scenarios or advanced checks. In this case, the agent is installed in one of your trusted MSC nodes that's already part of the baseline. So basic baseline checks is no longer helpful. If a legitimate message is sent by MSC, it will be processed normally. For example, the MSC is trying to send some update location message. If some inbound rumor is trying to attach to your network, TSG will check, this is a trusted node, it will allow the message. Then suppose the inbound rumor is trying to send a legitimate SMS. TSG will inspect the message. Again, this is a trusted node, and this is the source of this message. SMS message is an inbound rumor, verified inbound rumor, so the message will be allowed. Now, when the agent attempts to embed data in SMS-related messages, for example, the agent from the same MSC will try to send mobile-originated for the SS7 message and try to embed the data in these message parameters. TSG will detect this. It will identify the message is not related to a legitimate inbound rumor or roaming subscriber, and the attempt will be blocked. TSG also has a feature.
Ayman, sorry, just back to the previous slide, please. Yeah,
Yes.
just wondering, like, is there any firewall security solutions in the market that's be able to do such a roaming check? And based on your experience, is there any kind of like a approach or recommendations for the GSMA in particular for this roaming check approach?
Okay. Well, I'm not fully aware of all the other solutions, but from our observation, most signaling security products primarily focus on the inbound traffic direction, protecting attacks against signaling protocols that are coming from external network, not on the opposite direction, not for the outbound traffic. For GSMA, as far as I know, majority of the recommendations again covers the inbound traffic attacks originating from external networks. While some GSMA guidelines do mention performing checks for inbound roaming subscriber, this is again from the inbound traffic direction and is there mainly to help reduce false positives related to category 2 message checks or category 2 messages for attacks from originating from external. Generally, there is usually limited focus on monitoring or analyzing outbound traffic, which creates blind spots for certain attack scenarios. For instance, part of operator infrastructure might be compromised and used to send signaling attacks to other operators, or it can be used to extract data out of your network, as we already checked. Or it can be a third party leasing global titles from your global title ranges and start to use these addresses to perform some fraud operations or to launch attacks. So generally, most of the recommendations and solutions focus on the inbound traffic, not the outbound traffic.
Okay, thank you. It's clear. I think there's some gaps to be closed for most of the solutions. Okay.
Okay, now TSG includes another feature. It's called element profiling, which can detect deviation from normal traffic pattern of internal nodes. Okay. Again, we have some MSC that is trying to send some legitimate message. It will be allowed by TSG because it didn't find any problem with the message. But now for this scenario, we have an agent installed in the MSC. It's trying to mimic activities of liminal band. If we recall, they used some GTP emulators to create fake GTP tunnels in order to exfiltrate data, masking it as a normal subscriber traffic. So the agent will try to attempt to start a mobile data session by sending a message called update G_S location. At this point, TSG detects a deviation from the standard traffic pattern known for this node. This is a trusted MSC node, typically handling services like mobility, SMS delivery, some call routing or call handling functionality. However, it's now attempting to establish mobile data session, which is typically associated with other functionality like SGW, and as a result, attempt will be blocked. These approaches are just one way to detect tunneling. While we primarily focus on TSG, there may be other techniques that can be used to address these issues as well. That concludes our discussion. We are now open to any questions you might have.
Okay, Ayman, we have a question for you. So it's to address the issue of illegal nodes in the network. Is it possible to add an identifier tag to an SS7 node to distinguish a legitimate node from an obscured C2 server?
Yes, this is something that may work or may be possible. However, this is not a standard feature of SS7 nodes. You need custom changes for all of internal nodes, or at least an intermediate device that will intercept all the message and add these tags. And it needs a way to differentiate between legitimate nodes and any insiders or inside nodes. In addition, if an agent monitors the network and is able to identify this flag, it can be able to inject these tags as well. So a better way is to verify the source of the message itself, mainly based on the source addresses like IP address, like the global title, so that you can identify new nodes in the network, and also depend on the traffic patterns for behavior analysis. That's a better approach. Yeah. But this tagging can work, but requires some changes in the network.
Okay, also we have, so you initially mentioned the SIG translator tool by Liminal Panda. Do you think some of the data extraction methods discussed in this session are employed by that tool?
Okay, originally the report that discussed the Liminal Panda with its techniques didn't provide information. It was a report by CrowdStrike, didn't provide detailed information about how the tools works. So it's not clear how it works. And for this, why we are performing this research in order to try to identify all the possible ways that can be used for SS7. But again, since monitoring outbound connections or traffic is not widely deployed, I believe Lineal Panda can use some basic techniques. They don't need to add extra complexities to the exfiltration because usually no one is monitoring it at all.
Thank you. Any more questions? Okay, so one last question. Is there any simulation exercise lab available for vulnerability assessment? Please include both ACE and 5G lab in your response.
Yeah, maybe I can take this. Yeah, so yes, there is simulations available from our solution deck basically. So one of it is what we call ACE. Basically, is a breach and attack simulation tool. So what it does is it basically you can simulate the actual attacks via the IPX towards your network, or it can be done directly via your internal infrastructures as well through the routers. So on top of that, basically our ACE support like various of protocol is including like the SS7, diameter, GTP, and even like 5G. So for most of the MNO or even like or even like private network, you will be able to have such a breach and attack simulation tool that is particularly for the telecoms to environments, which you can have as a simulation tool. And on top of that, we also have a 5G lab. Basically, it's a lab that we have not only the software but also the hardware, including some of the virtualized core network or even like the radio access network, and also some of the user device. It has been all bundled together. It's like take it like a small gym where you can do like exercise in there, and you have like all the stacks where you can do the simulations within the 5G network itself. So yeah, basically these are some of the simulation tools that we have from our solution deck.
Okay, great. Thank you so much. And we're done with the webinar. We will be sharing a copy after the session. So thank you all for participating and joining. Thank you, Ayman and Sebastian.
Thanks,
Thank
Ferry, and thank
you.
you everyone for joining the webinar. Thank you.
Thanks.